This is a continuation of the previous video. Recall that this collection of videos is called Why Do We Want Sigma Additivity So Badly? And to answer that question, why do we want additivity? Well, first we want additivity in itself, but because it's related to continuity. And as we have just seen in the previous video, there are many interesting events that are defined in a limit. The first example we gave was of ruin probability, when we showed that in order to understand the probability that we will go to ruin at some point, then we had some union here of increasing sequence of events, and it turns out we could compute this probability by taking out the union and taking the limit instead. We have also seen that when we want to study convergence of random variables, we can express that in terms of unions, of intersections, of events, and to compute the probability of this complicated event, we can take limits of probabilities of much simpler events. And now we're going to study the interplay between continuity and sigma additivity for a measure or a probability measure. So the question is, why is sigma additivity important? Well, the first reason is it would be very strange not to have it. For instance, suppose we can analyze easily this variable capital T, this random variable that says the first time when something happens. And if we are interested in understanding the probability that that thing ever happens, well, we can just sum over all possible times t to be the first time when it happens. We sum those probabilities and then we get our answer. But there is a possibly stronger reason why we want probability measures to be sigma additive. It is that sigma additivity will make probability measures continuous. And we have spent the previous video just to convince ourselves that we really want a continuous probability measure. So that's a very good reason why we want sigma additivity. Well, and in fact, these two properties, which one? Being sigma additive and being continuous, they are equivalent, given that a probability measure satisfies the other axioms besides sigma additivity. It satisfies only finite additivity, then being sigma additive will be equivalent to it being continuous. We now go to the proof of this fact. So suppose we have a sequence, an increasing sequence of events. So increasing means a n is contained in a n plus 1 for every n. So we have an increasing sequence, and when we write it increases to a, that means a is the union of all these events. Suppose we have this increasing sequence and we want to understand what is the probability of A. Then we can come down here and write B1 to be A1, B2 to be just the difference, which is A2 minus A1, then B3 to be again the difference, A3 minus A2, and so on. So what are we doing here is we have a sequence of events. This sequence is increasing, it is getting larger and larger, and instead what I'm considering is the sequence of only the differences. Just this event first, then this event that we add to the top of it to get this one here, then this event that we add on the top of the two previous ones that will allow us to get this 1 here, and then finally this event that is even larger, yeah, we get this. So this would be B1, B2, B3, and B4. And what is important is these B's, they are disjoint. And most important, they have this property. If we take the first K events, the green ones down here, and we take the first K events, the red ones up here, what we get is the same. The only difference is these ones, they are disjoint, so we're really collecting pieces that do not overlap. And these ones, they are increasing, so there's a lot of redundance. So this will be the event A1, and here's the event A2 that is maybe just slightly larger than A1, and so on. But what matters is for every fixed K, the union of the first K events in this sequence down here coincides with this union of the first K events of this sequence up here. And this event is simply AK, the last one in the sequence here. From this identity, we can do the following. Replace K by infinity. So since this identity was true for every K, and this set here, they coincide and they are increasing, we can take the union over K, and we get this set, and this is simply A. And why is it so interesting? That's because by continuity, here we have probability of A, assuming our probability measure is continuous, it will be simply the limit in K of the probability of AK. And assuming we have sigma additivity, we get here simply that the probability of A equals the sum over K of the probability of BK, which by the theory of summing infinite series is simply the limit over K of the sum over N of this probability. Now, since these two numbers here, they are the same, simply because AK equals the disjoint union of B1, B2, B3 up to BK, and probability measures are finitely additive. So if this probability is given by this limit, it means this probability is also given by this infinite series, and vice versa. If this probability is given by this infinite series, then this probability is given by this limit. And this is why we claim that these two properties are equivalent, continuity and sigma additivity. So we really want sigma additivity either because we want it by itself, in itself, or because we want a probability measure to be continuous.